Fast Computer Vision Algorithms Applied to Motion Detection and Mosaicing, presentada per en Marc Vivet. Bueno, abans de començar per això, deixa'm dir-te que la sessió funcionarà d'aquesta manera. Primer tu faràs una exposició, aleshores hi haurà un torn de preguntes. Sorry. I'm explaining what I'm going to do. What we're going to do. First, there's going to be your presentation, of course, and afterwards there's be some questions from each committee member. And then we're going to deliver the final mark. This final mark can be pass or fail, but there is an addition to this mark, which is cum laude or not. And this depends on on some votation that we're going to do, secret votation, that we send to the scholar of the Doctorate, who then tells you at most 2 days later which is the final mark. Okay? So you can proceed.
Thank you. Well, this presentation is structured in 4 parts. We will introduce to the topic of motion detection, and we will present a new method for this topic. Then we will present another method for aligning the images in order to use the previous motion detector method when the camera is not static. Then we will present a new alignment method, the DLIG. And finally, we will show a method for generating a stereo mosaics. So in the left, you can see a scene of 3 trees, and in the right, it's the same scene, but it's a top view. So in here, you can see the camera and how the image is projected to the camera sensor. So motion detection consists on if there is something moving into a scene. So what we want to obtain is the motion mask, a mask that highlights the foreground respect to the background. So one way to obtain this motion mask is to generate a background image and then subtract this image to the current frame, and the regions with high difference are selected as regions with motion. And this kind of techniques, it's what it's called background subtraction. So if we look, now the problem is how do we construct this background image? So if we put the sequence in a space-time volume, we can see that concrete regions into the scene forms straight lines. These lines are called epipolar lines, and when the camera is static, these are parallel. And one way to obtain a background image is to study the most probable pixel, the most probable pixel value in one of these lines. So if we trace a line for each of the pixels in the video sequence, we can model each pixel as a simple threshold, a Gaussian, kernel density estimator, a mixture of Gaussian between others. So what we propose is we have seen that by generating a background image, we can extract the motion mask using the color, but we can also extract a mask showing where the shadows are located. In addition, we can do the same by the edges of the region with motion. So our motivation is to combine all these sources of information through a Marko random field in order to improve the final segmentation. So Marko random fields, it's a graphical model that are represented by nodes, and the relation between nodes are represented by edges. In our case, we use the factor graph representation that is equivalent to Marko random field. But in this case, the relations pass through another kind of node that is called factor node. So the joint probability of this function, it's computed as the multiplication of all the factors in the graphs. Then if we want to compute the probability of a concrete node, imagine that we want to compute the most probable state of X4, we have to compute the marginal probability of this state by assuming all the possible realizations of the network. And because there is not a direct link between X4 and X1, we can simplify the realizations thanks to the Markov property. The problem is computing the network like that. It's the complexity grows exponentially with the number of nodes, and thus becomes computationally intractable. It's for the reason that we use belief propagation. Belief propagation works by passing messages around the graph, and in our case, we use the sum product version. There is 2 kinds of messages. There is messages that goes to the nodes to the factor nodes, and then messages that goes to the factor nodes to the nodes. And the final marginal probability, it's computed as a belief that it's the product of all the messages that arrive to a concrete node. So now we will show how we have modeled our system. So if we look close to an image, we can see that there is two kinds of states that can have a pixel. So pixels can be from the background and pixels can be from the foreground. And we represent this as a random variable with two states. In addition, we can see that pixels from the background tends to be close to pixels from the background, and pixels from the foreground tends to be close to pixels from the foreground. So there is some kind of relation. We show the relation by connecting the node with its neighborhood through factor nodes. Then, in order to show the relation between the node and the observation data, one possible way is to generate 3 different nodes corresponding to each of the source data related to a function that converts the observation data into a probability. But in our case, we have simplified this method in order to make the formulation more simple. And we have only one observation data node that can have 8 states. So for instance, if 3 arrive, this means that the shadow detector is false, the edge detector is true, and the color detector is true, and then the function edge gives a probability for this case. In addition, we add temporal coherence, so we add another relation to the next and previous frame. So at the end, we have 6 connections to all the neighborhood of each pixel. So in order to summarize, we have a 3D Marko random fields where each pixel is denoted as a random variable with 2 states. This random variable is related by its neighborhood through factor nodes. Then we have the observation data that can have 8 states, and the function edge that converts these states into a probability. So in order to compute the most probable states, for instance, of the node x2 in a network like this, first of all, what we do is to propagate the messages from the observation data to the function edge. Then this function converts this observation data into a probability. Then the node sends the messages to the factor nodes. And finally, the factor nodes sends the messages to the node that we want to compute. So at the end, the probability of this state is the multiplication of the observation data multiplied by the messages that arrive to this node. And after this, we select the state with higher probability. This is a block diagram of our system. So using a video sequence, we generate the background image. And with this background image, we extract the color segmentation, the shadows, and the edges. And we combine all the sources of information through our Marko random field. Here is an example of the different inputs. So we have the color, the edges, and the shadows. And as you can see, the output is better than any of the inputs separately. So, okay. We have also tested in thermal cameras, and also works quite well. Here, the main problem is not the shadow because there is no shadows. But the problem in here is that the pixel values are very close together. But even this, it works quite well. So we have seen that when the camera is static, the epipolar lines are straight. So then we can study these lines in order to generate the background image. But imagine the case of a camera vibrating due to a strong wind. In this case, the lines are no longer straight. So generate a background image, as we have seen before, it's not possible. For the reason, what we need to do is to first select a reference frame and align the rest of the frame with it. And then restore the lines. But imagine this other case, a camera panning through a scene, okay? This is a PTZ typical example. So in this case, if we look at the first and the last frame, we can see that there is no regions in common. So it is not possible to directly align the images using only a single reference frame. For the reason, first of all, it is necessary to stitch the newly aligned regions in order to construct a reference frame which has a representation of the whole area. And this is what is called mosaicing, and the result is the mosaic image. So we propose to align the frames using multiple kernel tracking, which is a well-known and efficient and accurate algorithm. And instead of tracking regions of interest, that is for was proposed, the kernel tracking, we propose to track the whole frame, assuming that most of the frame will belong to the background, and the scene do not contain any parallax effect. So now I will introduce the kernel tracking. Kernel tracking works by representing a region of the image as a weighted histogram. and in our case, we weight the histogram using an Epenechikov kernel. Then we do the same into the frame that we want to compute using the same region. And then we have to minimize the sum of the scattered differences between the model and the new model that we have computed in the new frame plus an increment. So we linearize, we expand this part of here using the first order Taylor, giving this expression. And then where the jk is the Jacobian of the kernel, the derivative respect to x and y. And then by rewriting this part of here as m, and substituting this and setting this to 0, we arrive to a typical least-squares solution. So in the case of multiple kernel tracking, instead of generating a histogram of one single region, we generate multiple regions along all the image, and then we concatenate all the histograms into a single vector. We do the same in the frame that we want to align, and then now the objective function that we want to minimize is the minimization of these two big vectors. But the increment is common into all the regions. In this case, the minimization is as we have seen before, but the W in this case is all the M matrix that we have seen before concatenated. Multiple kernel tracking led us to estimate richer models, and this work we have extended multiple kernel tracking in order to estimate rotations and escalations. And this is done by derivating the kernel function with respect to the angle and the escalation. And we do that using the chain rule. So how it works, our method, we keep a representation of all the scene. Each square represents a weighted histogram, the weighted histogram corresponding to the region. And then if we want to align frame Fi, what we do is to use the previous aligned frame. We select the region that fits inside the previous aligned frame. We generate the module Qi, that is a subset of all the Q that we have. And then we generate the equivalent histograms from the frame that we want to align. After this, using the formula that we have seen before, we obtain the alignment parameters. And after this is aligned, we update the model in our global tracking model using the new aligned histograms. In addition, we add a mask in here in order to avoid using kernels that are placed in regions with motion. And we select these regions with the ones that has a high variance in its bins. So if a region has a very high variance in its bin, what we do is to remove all the bins in this histogram. So in addition, we keep the mosaic image, the background mosaic, and then we cut the piece that fits inside the new aligned frame. And using the previous method that we have seen before, we detect the motion. So this is an example of how the mosaic, the global tracking model is generated. The circles represents the regions that we keep the histogram. The green ones are the ones that are being used now. The violet ones are the ones that are keeping the model but are not being used. The red square is where the frame is looking, and we are aligning this image in here. And the white ones are the new ones that are added to our model. This is another example. In here, it shows how we detect motion with a camera that is not static. In here, you can see the background image, the input video, and the output that we get with our system. As you can see, the camera, even being moving, well, now it's not moving. So the camera is moving, and even being the camera moving, we are able to detect the regions with motion. Until the mosaic is being generated. Okay, since now we have seen that the image is generated by projecting the light into a plane. And the problem is that if this camera has a rotation, it's the typical case of PTZ cameras, this plane is different for each direction of the light. So until now we have used only translations, escalations, and rotations to align the images. But even having the same center of projection, if we trace two lights from the scene to the camera center, we can see that this light hits into different points of the planes. And only using rotations, escalations, and this, it's not enough to completely align these images. What we need to do is to backproject this, reproject these planes into a common plane, okay, where the mosaic image will be generated. And in this case, if we trace to right to left, we will see that the points fits perfectly. So our goal in here is to find the projective transformation Ti for each frame. Now I will introduce to the topic of alignment methods that can be divided using two concepts. So the information used to estimate the alignment, they can be direct or featureless methods, and these are the methods that use all the bilevel pixels to compute the alignment Ti, or indirect or feature-based methods that computes the alignment Ti by using a set of image locations. On the other hand, they can also be classified using the type of reference image that can be using the previous frame, then it will be a frame-to-frame alignment, or the mosaic image, then it will be a frame-to-mosaic alignment. The previous method that we have presented is direct or featureless method and a frame-to-mosaic alignment. So direct methods are very accurate, but they also require a very high accuracy or the computational time is very high. But this is not a problem at all in the case of video mosaicing because you can use the previous frame to initialize the estimation. In the case of indirect methods, can estimate complex transformation. Imagine if we have to obtain the 8 parameters of the projective transformation using the previous method that we have seen before. In this case, we will need to derive the Chekhov kernel for all these parameters, and this makes the computation very complex and with a high degrees of freedom. And this is not good. And then they not require an initialization, but they can need a very high computational time. In the case of frame-to-mosaic, frame-to-frame compared to frame-to-mosaic, frame-to-frame is a very simple method, and the computational time is very low because you only need to estimate transformations to frames that are close, and this is it should be very small transformation. But they accumulate error over time. If we look at a video sequence like this, where the camera can have loops in its trajectory, so and a small error it's produced at each alignment, and this error is propagated along all the sequence. So at the end, in this kind, if the mosaic has this shape, the misalignment can be very huge. So try to deal with the error accumulation makes the complexity grow over time because most of the methods try to keep all the frames in memory and then try to adjust all the estimations together. In the case of frame-to-mosaic, they require a very low memory. You only need to keep the mosaic and do not accumulate the error over time. The problem is that there is what we call precision degeneration. So imagine when we estimate the transformation between two frames, what we have is that the error produced in 2 points is similar because the transformation is very small. But in the case of aligning the frames using mosaic coordinates, the frames are distorted and the error are also distorted. So maybe a small error in mosaic coordinates can be a huge error into the frame coordinates. In addition, the frame needs to be warped before aligning, and this also introduces more computational time. And matching warped image, it also decreases the accuracy because the pixels are interpolated. So we propose to take advantage of the precision of direct methods, also take advantage of the simplicity of indirect methods to estimate complex transformations, prevent the error accumulation over time, prevent the precision degeneration, and maintain a low memory requirements. So why direct local, indirect global? Direct local because we use direct methods to align the small regions of the image to find point correspondences, and indirect global because we use the correspondences found in the direct local step to compute the transformation like in indirect methods. So the point correspondences that we use are from the mosaic to the frame in order to deal with the error accumulation problem. And we select the points of the mosaic that fits inside the frame using a t-hat that is an initial guess that can be the previous aligned frame. But the point is modeled using the original frame where the point was extracted in order to deal with the precision degeneration. So the model extracted, it's computed without interpolating pixels. Then, when we compute the equivalent model that will be used for a tracking algorithm, this model can be a weighted histogram, pixel intensity, whatever. This depends on the tracking algorithm. When we do that, the warp needed for compute the equivalent patch, it's compensated by the frame where the patch was extracted. And because two similar frames have similar transformations, at the end, the warping of the patch is very low. And then we find the parameters, the alignment parameters for each point, and closes under some criteria. So here, again, we have used kernel tracking, and we have tested different configurations using 1, 4, and 9 kernels to represent a region. As many kernels as better, but we have seen that 4 kernels it's enough in order to have a middle term instead of accuracy and computational time. In addition, in order to warp the region, we have tested these different versions using anisotropic kernels and an approximation using isotropic kernels. The problem of anisotropic is that you have to compute the kernel and the Jacobian at each iteration. And the isotropic version, you can pre-compute this and put it in a lookup table. And then you don't need to warp anything. You only need to place these kernels in the correct position. So you only need to compute the transformation of 4 points. So we have selected these 2 configurations. The DLIG computation works as can be seen here. So the first frame, we put this into Mosaic coordinates, and we generate 6 points. Well, any points, the points that we need to represent this. And then we model these points using the original frame after being warped. Okay, when we want to align a frame Fi, we select the points that fit inside the previous frame or the initial guess. And then, using the transformation of the points and the current frame, we find the warping of the regions inside the frame. Then, with the tracking algorithm, we find the point correspondences and a weight that is used to compute the projective transformation using weighted minimum squared error. This is an iterative process. So after this, we replace all the kernels and regions. We iterate and iterate until we find the final transformation. We warp the image, we place it into the mosaic, and we generate new locations into the mosaic. And then we model these locations using the frame after being warped before, sorry. So the criteria that we have used to weight the different regions is twice. It's the error given by the tracking algorithm and the number of times the reference point has been successfully used. We use this second criteria because the model of each region is updated during the time. So we believe in regions that has a lot of information. Because maybe when we create a new region, it's placed into a region with motion, and this is not what we want. This is an example. So from green to black, it's the weight of the regions. Violet, it's the regions that are not being used. And the rectangle, this is in frame coordinates, and this is in mosaic coordinates. And as you can see, when a car is moving across the screen, the weights of the kernels decreases. Okay, we also have made some quantitative tests in order to validate our method. So we have tested our method with the frame-to-frame alignment and the frame-to-mosaic alignment. In this case, it's a frame-to-mean mosaic alignment. And the graphics that you can see here, it's the mean of 8 different synthetic videos, and with 70 frames each, where the video it has a loop. So it starts from a point to another and then comes back to the same original point. So there is 70 frames for each video, and the error goes from 0 to 20 pixels. The red dots indicates the mean of all the errors and all the test. As can be seen here, the frame-to-frame accumulates error over time, as we have seen. In the case of SID, it's a very accurate algorithm, but when an error is produced, it's accumulated over time. In the case of frame-to-mosaic, the error is not accumulated as it was in here, but there is some kind of degeneration in the precision. And in our case, the error is maintained low during all the sequence, with all the tracking algorithms that we have tested using normalized cross-correlation, Lucas Canade, Sift, and Ransack. That is not a tracking algorithm, but it's well known and used for Mosaicing, and the one that we propose, the Kernel Tracking. In addition, using Kernel Tracking, in this case, we have tested the robustness through subit light changes. So in here, you can see the variations on pixel intensity. So from -5 to 5, this is aleatorious, to -20 to 20. And as you can see, the system is able to have some robust. There is a global illumination changes, so all the pixels are affected by the same random number, or a block. So the image is divided by 4 by 4 in a grid, and each of the blocks has a different intensity variation. In here, the results depends on the tracking algorithm. So we are using kernel tracking, and it's composed by bins. And in our case, we use 12 bins, and 12 bins corresponds to 20 degrees of grayscale. So the robustness of our system on this kind of subit changes depends on the tracking algorithm used. This is another example, but in this is a real case, a real mosaic that was a camera moving and coming during a sunset. And here you can see a comparison between the frame 150 and the frames 30,000, 37,000. And as you can see, the difference of color is very huge, but the system is able to align these two frames, even being very separate in time. In here, you can see the pixel difference of these two frames. You can see the lines are well aligned. So here is an example of the image. The mosaic is being constructed. As you can see now, the transformation is projective, and these are the regions we use it to describe the mosaic. And this is the previous example that we have seen before, but in this case, we are estimating a projective transformation. Now, as you can see, the lines are straight, because when you use a projective transformation, the lines are maintained straight. And it's clear that now the deformation is not, it's projective. Okay. So, following the same examples of the 3 trees, we can see that when the light arrives to the camera sensor, it arrives from different directions. And these different directions are projected into concrete regions into the CCD to form the image. So the idea is, if we have a video sequence, if we are able to generate a synthetic image of a concrete region of the CCD, we will be able to generate a mosaic or a frame of a concrete view of the scene. And if we generate two different mosaics corresponding to different positions in the CCD, we will be able to generate a stereo mosaic using a single camera. So following the same example, in order to construct this mosaic, what we need is a camera moving parallel to the scene. So in here, if we look at the space-time volume, we look concrete region, we will see that now the epipolar lines are straight, as it was in the other cases, but in this case, they are not parallel. And the slope of these lines depends on the depth of the object. So imagine this other example, a video sequence of a camera moving parallel. If we cut this volume from making a white-time plane, we will get a mosaic image. And if we do the same in the x-time plane, we will get the epipolar lines. If these lines are completely straight, the mosaic image will look very good. But in most of the cases, this is not the case, and the epipolar lines are not straight. So the output is very distorted. So now we will show how we have modeled this motion model. So if we track different regions into the scene, and there is no forward motion, no change of internal parameters, no rotations, no vertical displacements, and a constant velocity in the camera, all these constraints, then we will see that the epipolar lines are straight. This is a top view of this volume. And the epipolar lines can be modeled using the equation of a line. imagine that we remove one of these constraints, the constant velocity of the camera. If we again track different regions in the scene, we will see that the lines are no longer straight. So if we try to make this line straighten, and we use the previous methods that we have proposed, maybe this we will be able to make the red line straight, but then the blue line won't be straight. So what we need to do is to warp the time, because warping the time is step invariant. And now our motion model includes the increment of time. If we also remove two more constrictions, the rotations and vertical displacement, then the final motion model is the one that you can see here. So again, we are using kernel trackings in order to find the different epipolar lines. And in this case, we use the trajectory of the epipolar lines to compute the slope of each epipolar line. Okay, we do this for a lot of lines in the scene, and then we minimize all the regions together, but in this case, instead of derivating the curve in respect to the previously parameters, what we do is to derivate respect to the time, the vertical displacement, and the rotation of the camera. And again, we do this by computing the chain rule. In this case, the final solution in the least squares will be the increment of time, the increment of y, and the increment of rotations of each frame respect to the previous one. So in here you can see how the regions are tracked. So white means the new regions added. Green to red means the SSD error of the regions. Pink means the flat regions, and black means the regions which are discarded. And once we have all the video sequence aligned, it's time to construct the mosaic image. So as we have seen in the introduction, what we have to do is to cut this volume as if it wasn't a cake. And then, depending on the time of each frame, we will select a bigger or a smaller slope, strip. And then, depending on this, we will project this region into the plane that we have used to cut the volume and construct a mosaic like this. But as you can see, constructing the mosaic, as you can see here, have very huge problems, because you can see exactly where the strips are stitched, because the scene has parallax and the alignment is very difficult to be perfectly. So what we need to do is to try to hide this region by using some kind of blending. So we propose to use multiband blending. Multiband blending is a very well-known algorithm that works by using two images and a mask. And then if we combine these two images, we can see perfectly where the image is stitched. But with multiband blending, it's impossible to see where the images are stitched. So how it works, multiband blending works by decomposing the image in different frequencies and then apply a blending function different depending on the frequency of the image. So lower frequencies will have a very big blending and higher frequencies very small. But this is very problematic to implement this blending when you have a very narrow stitch, because you need to compute the pyramid of blending. So you need a very big area for computing these different frequencies. So what we propose is, instead of stitching each strip separately, what we propose is to simplify the problem and compute two mosaics. And after compute two mosaics and a mask, and then combine all together using a single pyramid blending. So in here we have the odd, the even, and the mask, and we will construct a mosaic for the odd frames, another for the even frames, and at the same time we will construct a mask. So we will start by the frame 1, which is odd, and we will compute this. We will generate the odd frame and the mask. Then the next one is even, so we will compute this. As you can see, the mask starts from white to black, and then black to white, and so on. So this is done for all the frames in the video sequence until you have two mosaics and this kind of pattern. So once you have this is the mosaic without blending. And with blending, as you can see here, you can see the strips, and here are hidden. This is another example. Here you can see the strips. This is maybe more clear, and here are hidden. But the detail is preserved. So, and this is a big example. So you can see the odd frame mosaic, the even frame mosaic, and the mask of this big mosaic. And this is the result without blending. As you can see here, it's very clear where the strips are put together. But with blending, these strips are hidden, and as you can see, it's more soft, but the detail is preserved. So you can see. Okay, this is another example, but in this case, it's cutting the volume in a lot of different views and making this effect. And also, we have implemented this method using an iPhone application, and these are some results. And this other. So we have presented a new background subtraction method, which let us to combine different sources of information to improve the motion segmentation. We have proposed to use multiple kernel tracking to compensate the image in order to apply background subtraction on the scenes where the camera is not static. We have presented a new alignment method, the DLIG, which combines the best characteristics of direct and indirect alignment methods. And furthermore, the method presented is able to deal with the error accumulation problem and the precision degeneration. We have presented a new method for stereo mosaicing based on feature tracking, and in addition, we have presented a method for applying pyramid blending on images composed by narrow strips. As a future work, we propose to implement the presented algorithms using CUDA, OpenCL, or OpenGL. Some of the tests reveals that these algorithms can be 100 times faster, increment the accuracy of kernel tracking, for instance, by combining its result with Lucas Canary approach, explore the camera motion, for instance, creating 3D real mosaics, and new blending methods, which can be the combination of our barcode blending plus graph cuts. These are the publications that I have been part of. That's all.
Questions and also to express their opinion on your manuscript and presentation also.
Okay.
Can I start with
thank you very much, Marc, for your presentation. I consider that the presentation is excellent. The presentation helped me to understand a little bit more your document and to go inside your results. In my opinion, the results are very nice, impressive, but let me try to comment some different things related to all this. Of course, I said that the results are very good. It seems that are very nice and very good, but I have a question about the general experimental results that you present in the document and here in the room